All right, by now you have gone to all the contact force stations, and it's time to wrap up the foldable notes that we started the other day. So if you would, open up your lab notebook, and we're going to start at the beginning of contact forces, though I know some classes might have gotten a few of these done already. And remember that we're going to flip the flap, and on the back of the flap, you'll be putting the symbol as well as the definition. And then I'll also bring in some of the evidence from the stations that you should have picked out. So the first one that we have is all the contact forces. Now, the contact forces, I just want to emphasize, you must have contact in order for these forces to be present. So if there's no contact, there will be no force. First one is force push-pull. The symbol is FP, and really this is the biggest category for forces because we do a lot of pushes and pulls on objects every single day. Now I like to think of a push-pull force. The source of that is typically going to be a person, and you'll notice in a little bit later some of the other ones the source won't be a person, it'll be something different. So definition, write it down. Symbol, write it down. If the substitute needs to pause the tape while we go, then just let them know if I'm going too fast. Examples of push-pull force, the list could go on and on and on. Once again, each time that you see the push-pull, notice it's a person that's doing this. So a person pushes a box, hitting a baseball, shooting a basketball, shutting the door, pulling out a chair. That person is providing a push or pull force on those objects. Now, as far as a push force on every single one of the stations, the first station, you were using your finger and you were pushing on the ruler. The fourth station, you had a bucket of water. You were pushing on the ball as it went submerged into the water. Some of you might have called a push on the pogo stick because the person's feet were pushing down every single time. All of those would be good examples of push forces. Once again, this is the largest category. The next one that we have is force normal. Force normal, look at the symbol, F sub n. And often I will use the word support force for force normal just to make it easy. It is a support force, and it is a support that is provided by a surface. Now, once again, we have to look at the source of the force. Now, a surface might be a table, a floor, a wall, some kind of surface that's doing the supporting versus a person's hand. Okay, so if it is a surface that is doing the supporting, then it would be a normal force. Now the reason they call it a normal force is because it always acts at a 90-degree angle to the surface. Normal means 90 degrees. And when I get back from Boston, I will show you, I've got a normal force finder that can help you figure out exactly where the normal force is going to be. Now, if you take a look at the examples that I have, if you're sitting in the chair is supporting you. So the chair is providing that support force that is going up. Once again, I'm using the word support force as normal force. Now, it is 90 degrees with the surface. Again, if I lean against the wall. Now, my surface this time is going to be the wall, and so if you notice where the arrow is pointing at a 90 degree to support. Now, you know that the normal force is coming straight out from the wall. The reason you know that is because if the wall were to disappear, well, then the person would fall. Now, evidence from the stations. First of all, you had the ruler was supporting your finger. You had the cans were supporting the ruler. You might have even looked at the normal force with the pogo stick. If you think about what supports the pogo stick, every time it hits the ground. When it was in contact with the ground, then you would have the normal force. If it's not in contact with the ground, there would be no normal force. The bucket was being supported by the table. Now, what's also very interesting about a normal force is simply by looking at all the different directions it could go if it is in 90 degrees with the surface. Now, if you take a look here at this animation, we have force gravity that's going straight down. But as you notice, as you watch, the normal force, the direction of the normal force continues to change. It changes the entire time. And if you'll notice, it is always going to be at a 90 degree with the surface. 90 degree with the surface, so that's why the angle of the normal force changes. And that'll come into play a little bit later when we connect it with acceleration. All right, next one. Force tension. Now, once again, think about the source of the force tension. Force tension would be any kind of support by a string, cable, wire, or rope. It is a support by a string, cable, wire, or rope. So once again, you have to look at the source of the force. If it's a rope, you know it's a tension force. Now the other thing about tension is that it always acts back up the string, and you're going to see that on the examples in a minute. Once again, substitute if you need to pause at this point for students to write down the definitions, feel free to do that. Now if you'll take a look at the pictures, we have the boxing gloves, and we have the boxing gloves that are just hanging from string. Now if I were to cut that string, those boxing gloves would fall, so therefore you know that the tension is going back up the string. A lamp from a ceiling, if it's hanging from a cord, if you've got a fish caught on a fishing line, those are things to think about with force tension. Now, tension force. I did not have a single station that had any ropes, cables, or wires. So there was no evidence whatsoever on the stations of any tension. Since there was no evidence, then I would recommend on the back of the flap on your lab notebook to write a few of these examples, with a picture is fine, to remind you that the source of a tension force must be a rope, cable, or a wire. Next one, elastic. Force elastic, F-E-L, is the next force, and it is a contact force. And basically the point behind an elastic force is it restores an object to its original shape after being stretched or compressed. Now, if you think about what kind of objects would have sources of elastic force, it would be anything that stretches and returns to its original shape. Okay, so when I think of elastic force, I'm going to be thinking of things that can stretch or compress. So a rubber band, you can stretch it. A spring can do both. A spring can actually stretch or compress, and a bungee cord can stretch. Muscles are going to contract as well, stretch and contract. So in this case, I would say all those would be elastic forces. Now, for our sake, we are really going to be sticking with the pure sense of something that stretches or compresses. So I like to think of elastic forces are the kind, obvious examples. For example, in your stations, you had a spring. That spring would be the most obvious example of an elastic force. Now, some of you were trying to say that the ruler would be an elastic force, and I don't deny that when you flex the ruler, it does return to its original shape. So I don't disagree with that. What we'll do in this class, however, is we will use true examples of elastic force that really are not very debatable. For example, the springs, bungee cords, things that will either clearly stretch or compress. Next one we have is force friction, F sub F. And the idea behind force friction is that it's an interaction between two surfaces that oppose motion or potential motion. The misconception here with friction is that you have to be moving in order to have friction, and that's completely false. You have to have the potential to move, and I'll talk about that here in just a minute. Once again, it's two surfaces that are interacting. Classic example of friction would be if two hands are rubbing against one another. Okay, that's what warms your hands up. If you have a rug burn, sliding into home base, cleats and otherwise just shoes on the floor. If we didn't have friction, then we would not be able to walk. Now, if you take a look at the different examples of shoes I've got, every sport has different kinds of shoes. Some of you that play sports are going to recognize your shoes on the screen up here. And if you'll notice, a baseball cleat is going to look very, very different from a track cleat. Those cleats are designed to work in conjunction with the particular surface that a person is running on. And so if you're a football player and you're on turf, you'll have a different set of cleats than if you are playing on a natural field. Again, if it's muddy or not, it will change the type of cleat that you use. Now, as far as two surfaces interacting, we didn't have any examples of that in our stations. So once again, since there were no examples of friction, feel free to go ahead and write down these examples that are provided here. Friction isn't always bad, right? Friction can be very helpful, and I think that's an important thing to understand. Next one we have is buoyant force. Buoyant force is a support force, and it is a support force by water or other gases. We call this fluids. So water and other gases would be an example of buoyant force. Now, many of you might have heard of buoys that hang out at the lake that can mark no-wake zones or shallow areas. And a buoy is just short for buoyant force. So any fluid that could be a lifting force, so a hot air balloon is a great example of a fluid. That fluid is hot gases. Floaties that you blow up and put in the pool, and just simply boats. Water is an excellent example of a source of buoyant force, as well as hot air or helium. So once again, always trace back to what the source of the force is. If it's water or fluid or gases that are a lifting force, then that would be classified as a buoyant force. You had one example of buoyant force in the water, a bucket and water, and it was actually in two places. The first place with the bucket and water and ping pong ball was when the water was supporting the ping pong ball. That water was supporting the ball and was a great example of buoyant force. Some of you might have even said that the gas on the inside of the ping pong ball could be a buoyant force as well, because it's similar to that hot air balloon. You've got gas on the inside of a substance, so therefore it is less dense, therefore it will rise. My guess is that most of you just picked out the water as being the buoyant force. Last one, air and water resistance. We have two different symbols for this, AR, air resistance, or WR, water resistance. And this is not to be confused with a push, right? So this is a resistant force, and it is an interaction between an object and water, or particles in the air that oppose motion. Now, the idea behind this is that you have to have motion in order for this force to be felt. You have to have motion in order for this force to be felt, which is not the same thing as friction. And so it is important to keep them separate. Now, drag on a car, that's just air resistance. Drag on a swimmer doing laps, that's water resistance. And so those are basically, as you're moving forward in the air and the water, you have all those particles that are bouncing into you. Now, if you take a look at this swimsuit is designed to reduce water resistance. It's designed to be very sleek, and the cap is also worn just to prevent drag. You want as small amount of drag as possible if you are a swimmer. Again, you want to have aerodynamic cars, and you want to maximize that air resistance in this situation by making sure that you have an extremely aerodynamic car. If you have a really large car, an SUV versus a smaller car, often your gas mileage is going to be reflected to be higher in the SUV for various reasons, but one of them is you have a lot more air resistance, and in that case you're going to burn a lot more fuel. Evidence for air and water resistance, once again, we didn't have any. Since we didn't have any, you'll want to make sure that you go through and write the examples down that are provided so that you have something under the flap for each one. Once again, 7 contact forces. The idea behind every one of these is you have to think about what the source of the force is. If it's a force normal, it would be a surface doing the supporting. Tension would be a string. Elastic would be a spring. Friction are when two surfaces interact with one another. A buoyant force would be a water or gas. And then, of course, air and water resistance can only happen whenever you are moving. Good luck on the next set of stations.